Hello everyone, let us begin 7th lecture, and in our 7th lecture we will now start looking at electrochemical nature of corrosion and its thermodynamics. So, lecture 7, electrochemical corrosion and its thermodynamics. Now, when we talk about this electrochemical nature, we will bring in the examples what we have already discussed in our earlier lectures. The example is, if we have a zinc plate dipped in dilute HCl solution, and this is a zinc plate, let us say. Now, once we put in that zinc plate, we see that the bubbles are forming on top of zinc surface, and these bubbles are nothing but hydrogen gas. Now, if we analyze this particular reaction, because these bubbles are forming because of some reaction, then we will see that one reaction is this one. This is anodic reaction, or we call it oxidation. Now, two electrons are released by zinc atom and it goes to zinc ion. Now, electrons cannot remain free, it has to be balanced by some mechanism, because the total amount of charge is constant in this universe. So, we call it charge conservation. So, these electrons will be accepted by some other reaction. The other reaction is nothing but H plus 2E, it goes to H2. Now, this is reduction reaction, and we also call it cathodic, and this is anodic. Now, if we combine them, then we will see that 2H plus Zn, 2 electron, these two are cancelling each other. So, that means we are maintaining charge balance, and then also we are maintaining the conservation of charge concept. So, that becomes H2 plus Zn plus plus. Now, this is the complete reaction. Now, as we have understood before, that when some metal atom converts to metal ion, so it goes into the solution, and that one we call it corrosion. This is nothing but corrosion. So, oxidation is nothing but corrosion. Now, in this case, interestingly, this is the complete reaction. This is the complete reaction, or if we consider the another species that is present in the solution, which is chlorine ion. Now, that chlorine ion will react with zinc plus plus, so it will form zinc chloride. So, the complete reaction we can also write in this form: 2HCl plus Zn equal to Zn plus 2Cl minus plus H2 . So, this is another way to write the cell reaction. So, here I am sorry that we missed one plus sign here, and finally, from this we can write this reaction. Now, this is the complete cell reaction, and in order to have this complete cell reaction, we have to have two reactions, one is reduction, another one is oxidation. They are running parallelly. Now, interestingly, if we see in the reduction, if we take only the rate part, and in the oxidation, if we take only the ox part, if we connect them, then it becomes redox. And when we have redox reaction, then only we have these complete reactions. So, for the complete cell reaction, which is nothing but the redox reaction, it has got one reduction reaction and one oxidation reaction. And when we have this redox reaction, we have the corrosion of zinc in the form of zinc plus ion. And this redox reaction is important in the sense that only oxidation cannot take place or only reduction cannot take place. See, if there is one reduction reaction, there must be one oxidation reaction, at least from this particular example it is very clear, and then only we have complete cell reaction. And interestingly, in the redox reaction, we have the number of electrons accepted by reduction is equal to number of electrons generated or released by oxidation reaction. This is very important aspect, and that maintains the charge balance and also the charge conservation. Now, this also reflects a kind of rate thing in rate kind of aspect. Rate means per unit time. Now, if we have this particular reduction reaction happening at a different rate than the second oxidation reaction, then there will be a cumulative charge conservation, charge consumption, cumulative charge consumption. This is nothing but the consumption, and this is generation. So, what I am considering that if we have more amount of the number of reactions of this first reaction, which is reduction reaction, happening at a much higher rate compared to the second reaction, which is oxidation, that means at any given time we have more amount of electron consumptions than the generation. So, which will not maintain this charge conservation. So, in order to maintain charge conservation, the consumption of electrons per unit time should be equal to generation of electron per unit time. So, the rate of reduction should be equal to rate of oxidation, and since oxidation is nothing but corrosion, so it becomes rate of corrosion. This is extremely important concept. The rate of reduction is equal to rate of oxidation or corrosion. Now, if we go to see some other considerations, for example, in this situation, the example what we have considered in the previous case, you have zinc and same HCl solution dilute, and in this if we have, let us say, if we have little bit of FeCl3, a small content, it is considered as impurity, then the situation would be different. Now, before considering this situation, as we have seen that if the previous case, if this particular condition, if it is happening at a particular temperature and pressure, if we maintain the temperature and pressure and if we make it a closed system, so this reaction, this particular reaction would reach to equilibrium. Now, when it reaches equilibrium, then this reaction, it also reaches equilibrium. So, now if we consider this particular reaction, the forward reaction is nothing but the reduction reaction. So, this is reduction. Now, if we remove this part, so then it becomes only red, and interestingly reverse reaction is nothing but oxidation, and if we remove this part, then also this becomes a redox reaction. So, combinedly it becomes another redox reaction. Now, in the beginning, of course, hydrogen gas generation would be very fast rate. Now, if we consider the rate criteria, time, rate, in the beginning we have huge amount of hydrogen ions in the system. So, the rate at which hydrogen gas will be generated will be very fast in the beginning, and as we have time lapses, then the rate will decrease and it will be like this. It will flatten out, that means it reaches steady state. Now, when this particular thing is H plus 2 equal to H 2. Now, once we have a generation of hydrogen, the reverse reaction would start happening. So, the reverse reaction would take place now. Initially, it was almost no hydrogen gas. So, it will start with a 0 and then it will also merge with this particular rate. So, this is H 2 minus 2 equal to 2 H plus. So, this is the point where it reaches equilibrium. So, the rate of forward reaction is exactly same as the rate of backward reaction. Similar situation can arise, zinc plus, zinc can go to zinc plus. Here the forward reaction is ox and the backward reaction is red, reduction. So, this is also a redox and it also reaches equilibrium when the system reaches equilibrium. Now, interestingly, for this complete cell reaction, 2H plus Zn equal to Zn plus H2, it is combination of this reaction and this reaction. These two reactions are electrochemical in nature because it involves electron acceptance or electron release, and they are called half cell reaction. So, this is half cell. This is one half cell, this is second half cell. Which combines and then forms a complete cell reaction. Now, coming to this example, when we have dilute HCl and we have little bit of FeCl3, in the previous case we have one reduction and one oxidation. Now, interestingly, in this case there will be one additional reduction reaction. Now, let us see what is that additional reduction reaction. First in this case, first reaction would be definitely 2H plus 2E equal to H2. This is the same as what was considered before. Second reduction reaction, which is Fe3 plus accepts one electron and it goes to Fe plus Fe2 plus. This is also a reduction reaction. So, these are two reduction reactions. And there will be only one oxidation reaction, which is zinc plus plus. This is oxidation reaction. Now, as we have mentioned that there should be a rate of reduction reaction should be equal to the rate of oxidation reaction. Now, here we have two reduction reactions. So, you need more electron supply for those two reduction reactions. So, where from this extra electron would come to take care of two reduction reactions? It has to come from this reaction. So, the generation of or release of electron from zinc atom would increase, or at the same time the rate at which zinc would release electron would also increase. It means that the rate of zinc dissolution would also increase, and finally, it suggests that the corrosion rate of zinc increases. So, we have a system where we have multiple number of reduction reactions. So, here two reduction reactions, two number and one oxidation, and that would increase the rate of corrosion. And exactly that is observed when we have zinc in the solution of dilute HCl, where we have little bit of FeCl2 Cl3 impurity. And of course, temperature and pressure both are same, both are maintained same. Now, in this case we can also have a consideration of dissolved oxygen. Now, if it is containing dissolved oxygen would also allow another reduction reaction. So, this reduction reaction for this case, since it is acidic medium, so then the reduction reaction involving oxygen would be this will be the reduction reaction, and this is a very strong reduction reaction. So, we are having one more reduction reaction. Now, in this system we have three reduction reactions and one oxidation reaction. So, in order to maintain the electron supply for three reduction reactions, the number of atoms of zinc going into solution by releasing electron for the reduction reactions would also increase per unit time. So, the rate of oxidation or the rate of corrosion of zinc would further increase. So, as we see these three examples, that in a system we can have one reduction and one oxidation, or there could be multiple reduction reactions and one oxidation, but the total number of electrons supplied by the oxidation reaction would also increase, because we have to maintain three reduction reactions. But at the end we have to maintain the total rate of reduction should be equal to total rate of oxidation. So, this particular concept will be clear and it will be quantitatively understood when we talk about mixed potential theory. So, this is a consideration where we have one reduction, multiple reduction reactions and one oxidation reactions. We can have a situation. So, this particular thing we are having, if we try to see a situation. So, multiple reduction reactions and one oxidation reaction. All three examples. Now, we have example like where we have one reduction reaction, but there could be multiple oxidation reaction. The classic example is if we have iron and zinc, this couple, this galvanic couple is placed in acid, let us say HCl acid. The situation would be like there would be one oxidation reaction, and if this acid HCl is pure as well as no dissolved oxygen. So, then we do not have any other reduction reaction except hydrogen reduction. So, this reduction reaction would take place, and two oxidation reactions are Fe zinc, these two oxidation reactions. Now, interestingly, when we have individually iron is dipped in HCl or zinc is dipped in HCl, their corrosion rates are considerably high. But once we have this situation, a galvanic couple of iron and zinc are dipped in, if that couple is dipped in HCl, then we have both these oxidation reactions going on and one reduction reaction. But interestingly, that time our observation, after some time if we take it out that couple and try to analyze, we will see oxidation of iron is minimized in couple condition as compared to when iron is immersed separately in the same acid. But at the same time, if we see the zinc, oxidation of zinc would increase rather in couple condition as compared to when zinc is immersed separately in the same acid. So, what we are saying qualitatively, but when we talk about mixed potential theory, we will also quantify that how much would be the reduction of iron, reduction of rate of oxidation of iron, or how much would be the increase of oxidation of zinc. Here the reduction means I would say when how much would be the lowering or decrease in the oxidation rate of iron and how much would be the increase in oxidation of zinc when we have a couple and that one is dipped in HCl solution. And this is the very concept of sacrificial effect of zinc. And here also redox reactions are taking place. Here redox reaction, we consider redox reaction. In this case we have 2 ox 1 red, but in our earlier situations this is 2 ox and 1 red, or I would consider, since we are talking about redox not ox red, so we can put it as 1 red 2 ox. This is the example, couple of iron and zinc dipped in acid. Now, in the previous situation all 3 examples, this is example 4th, example 3 was zinc dipped in dilute HCl containing FeCl3 and dissolve oxygen, where we have 3 red plus 1 ox, 2 zinc dipped in dilute HCl plus FeCl3. We have 2 red reduction and 1 oxidation reaction, and finally, in the first case where zinc dipped in dilute HCl, we have 1 reduction and 1 ox. So, like that there could be number of oxidation reactions and there could be number of reduction reactions in a particular cell, but finally, we have to make sure that we have to see that the rate of total reduction should be equal to the rate of total oxidation, and because that total rate of reduction and total rate of oxidations are same in order to maintain charge conservation. So, in these 3 cases we have increase in zinc dissolution. As we go upward we have more and more zinc dissolution, but in this case we have a sacrificial effect of zinc. Iron dissolution decreases or minimized and zinc corrosion increases, and that is the very concept of sacrificial anode nature of zinc on iron surface. So, let us stop here. We will continue our discussion on electrochemical nature of corrosion. Thank you.